Good day, everyone. Good day to our Calculus 2 instructor, Mrs. Villamor, and to our classmates. We are the Group 3, and for today's video, we're going to discuss work by integrations or work as an application of integrations. I am Charmaine Marie A. Arubo from BSIE 1B.
I am Claire Bakiran from BSIE 1B.
My name is Joselito Saruna in BSIE 1B.
And we are the Group 3.
What is work? It is a fundamental concept in classical physics. If an object is moved in a straight line against a force for a distance, the work is done is W equals Fd, or work equals force times distance.
The concept of work is work equals force times distance. So this will be our concept for today's discussion. The application of force that we are going to discuss is work done by a spring. So the spring had a length which is L. So if we are going to apply force in it, tension, it will elongate distance x. So we can say that work is equal to force times distance. So in derivatives, we can say that differential of work is equal to force times distance. In spring, we have this concept called spring constant key, wherein it is actually force per unit of elongations. So if you are going to apply force in it, it will elongate at a certain distance x. Therefore, we can say that force is equal to kx. So we are going to substitute it here. So differential of work equals force, which is kx, dx, wherein k is constant, and let's integrate both sides. Work is equal to k, the integration of x dx, from the elongation of x sub 1 to x sub 2. The elongation here, which is the x sub 1 to x sub 2, is of course the reference point here is the original length. So, work is equal to k, apply power formula, x squared over 2 from x sub 1 to x sub 2. So, this is our formula for work done by a spring. So, let's try example. Find the work done in stretching a spring of natural length of 10 cm from 12 cm to 15 cm. Assume a force of 8 Newton is needed to hold it at a length of 12 cm. So the original length of the spring is 10 cm. Our x sub 1 here, which is the initial elongation, so this is from 12 cm to 15 cm. And since 10 cm is our reference point, we can say that 12 cm minus 10 cm. Our x sub 1 is equal to 2 cm. Next, our x sub 2, which is the final elongation, so this is the total of 15 cm. Since our reference point or the original length is 10 cm, so x sub 1 is equal to 15 cm minus 10 cm. Our x sub 2 is 5 cm. So our x sub 1 and x sub 2, this is our limits. Now, assume a force of 8 Newton is needed to hold it at a length of 12 cm. So, you have K equals force per unit of elongations. So, obviously, our force is 8 Newton over our elongations is assume that it is 12 centimeters. So, 12 centimeter and our reference point or the original length is 10. We can say that 12 centimeter minus 10 centimeter. So, 8 Newton over 12 centimeter minus 10, 2 centimeter, which is 4 Newton per centimeter. So this is our key. So let's apply the formula. Work is equal to 1/2 k x sub 2 squared minus x sub 1 squared. So 1/2 k, which is 4, x sub 2, which is 5 squared minus x sub 1, which is 2, so 2 squared. 1/2 times 4, 2. 5 squared, 25, minus 2 squared, 4. So, 2 times 21, or 42 Newton per centimeter. So this is our answer. And take note that the fundamental unit of work is joule, which is Newton per meter. Since our answer is 42 Newton per centimeter, let's convert Newton per centimeter into Newton per meter. So work equals 42 Newton per centimeter. Apply the conversion. 1 meter is equivalent to 100 centimeter. Cancel centimeter. 42 times 1, 42. 42 divided by 100, 0.42 Newton per meter, or 0.42 joule. So this is our final answer. 0.42 joule.
A force of 60 newtons is required to hold a spring that has been stretched from its natural length of 12 centimeters to 17 centimeters. How much work is done in stretching the spring from 15 centimeters to 20 centimeters? So the first thing we need to do is calculate K. So we have known that the force required to hold the spring beyond its natural length is K times X is the distance between where you hold in a spring and its natural life. So let's say this is the natural line for the spring, that 12 centimeters. And we stretch it beyond its natural length. So this distance here, that X 17, is the total distance between point A and point B. X is the difference between 17 and 12. So in this example, X is 5 centimeters when a force of 60 newtons is applied. So 60 equals K times 5. So K is going to be 60 divided by 5, which is 12 newtons. And it's newtons per centimeters. Now, let's get K in newtons per meter. So, let's convert it. 5 centimeters to meter. 1 meter is 100 centimeters. So, 5 divided by 100 is 0.05 meters. Now, K is 5. Now, K is F divided by X. So, we have 16 newtons divided by 0.05 meters, and so that's going to be 1200 newtons per meter. So that's the force in terms of X as a function. K times X, or 1200X, so the work required is going to be the definite integral from A to B. But we're comparing these values to its natural length of 12. So the difference between 12 and 15 is 3 centimeters. The difference between 20 and the natural length of 12 is 8/17. Or 0.08 meters, and then it's going to be f of x dx. So the antiderivative of x is x squared over 2 evaluated from 0.08 3 to 0.08, and 1200 divided by 2 is 600. So we have 600x squared. So now let's plug in 0.08. So it's 600 times 0.08 squared times 600, that's 3.84, and 0.03 squared times 600 is 0.54. So the final answer is 3.3 joules, and so that's the work required to stretch the spring from 15 centimeters to 20 centimeters.
So the next example is a force of 50 pounds is required to hold a spring stretched 5 inches beyond its natural length. How much work is required to stretch it from its natural length to 10 inches beyond its natural length in feet-pounds? So this is the formula first. So we're going to base the formula of F is equal to Kx, which is K is the spring constant, while X is the distance between its natural and current lengths. So let's first find the K first. So in order to find the K first, the formula is K is equal to F over X, which is force divided by its X. Okay, so the force in the problem is 50 pounds while the X is 5 inches. So 50 pounds divided by 5 inches is equal to 10 pounds per inches. 10 pounds per inches. So again, so let's return to the first formula. So F of X is equal to the K, which is the 10 pounds per inch times X. So, and the next formula is, which is work. So work is equal to the definite integral of A from A to B of the force functions times dx. So the A is equal to 0 while B is equal to 10, and f of x is 10x dx. So the antiderivatives of 10x is equal to 10x squared over 2 evaluated from A to B, which is 0 to 10. So let's evaluate. So 10x squared divided by 2 is 5x squared evaluated from 0 to 10. So 5 times 10 squared minus 5 times 0 is equal to 500 pounds per inches. So the needed measurement is feet per pounds feet or feet pounds. So we're going to convert the inches into feet. So 50 pounds per inches will be multiplied by 1 feet over 12 inches. Then cancel the both inches, and the remaining is 500 over 12 feet pounds. So the 500 divided by 12 is 41.67 feet pounds. So the final answer is 41.64 feet pounds.
How much work is required to lift a 5-kilogram book a 2-meter high above the ground? The formula of work is work equals force times distance. Let's recall that the formula of force is force equals ma, wherein m is a mass and a is the acceleration, or mg, wherein g is the pull of gravity, which is 9.8 meter per second squared. So let's use this one. Work is equal to mjd. Substitute, m is 5 kilograms times the pull of gravity, 9.8 meter per second squared and the distance of 2 meters. So, 5 times 2, 10. 10 times 9.8 is 98. 98 kilograms times meter squared per second squared or 98 joule. So, this is our final answer.
An inverted circular cone with a height of 12 meter and a radius of 5 meter is filled with water to a height of 9 meter. How much work is required to empty the tank by pumping all of the water to the top of the tank? So, nag-drawing ko diagram ari. Then, ang height sa, as you can see, the height of the cone is 12 meter. And the height of the water inside the cone is 9 meter. And the height between the below the cone and above the surface of water is 3 meter. And the formula that we're going to use is kanang the density times the gravitational acceleration, definite integral from A to B, and of volume x times the distance dx. So before that, yun sa nako pagkuha ni nga formula ha. So magkuan sa sunugdanan. So we already know nga work, ang formula sa work is force times distance. So in order, ang formula sa force is equal to mass times gravity. So F will be changed into mass times, will be substitute sa kuan, which is the mass times gravity times the distance, which is capital na nakog D para di kayo maglibog. So W is equal to M times G times D. And in physics also is ang density is the formula of the density is mass over volume. And in order to find the mass is atong i-cross product, so mass is equal to density times volume. So since nakuha na to ang another nga formula sa mass, so ang mass na ari sa formula nga isa is atong i-change na sad sa density times volume. So ang mahikuha na is work is equal to density times volume times gravity times distance. So mao ni siya nga final nga formula, which is kani. So let's go back to the problem. So sa makita na to sa, so the formula of work is kani sad. So makita na to nga need ang volume. So we already know sad nga ang formula sa volume sa cone is pi r squared times height. So we need to find the volume first. So dirita, so akong i-specify lang kung asang volume. And also this is the, so this is the delta x. So since wala pa may gihatag nga distance, so ato nga pangitaon is, so makita na to during a triangle kare. So there is the money ang r, which is kani. Then ang measurement na to sa ang height na to ron sa ani is 12 minus x, since ang overall nga height na to is 12 and atong radius is 5, and which is the kani r. So mo-consider siya nga r r over 12 minus x is equal to 5 halves. So ani proportional. So atong i-cross product, which is i-multiply na to by both sides by 12 minus x. So ang result the result will be R is equal to 5 over 12 times 12 minus x. So, nakuha na nato ang radius. So, kaning radius na to is atuan na siyang i-substitute sa formula na to sa volume. So, the volume is equal to pi times 5 over 12 times 12 minus x squared. Squared na to ang radius times delta x, which is ang height. So, the volume is equal to 25 pi over 144 times 112 minus x times 2. So, kung maglibog mo kung giunsa na ko pagkuhang 25, so get 25 squared and ang 12 squared is 144. Dx. So, since nakuha na to ang volume, so let's go to the final nga formula, which is ang work. So, let us substitute na. So, work is equal to, so ang density of the water is 1000 cubic per meter and the gravitational acceleration is 9.8 meter per second. Definite integral from 3 to 12, 25 pi over 144 times 12 minus x squared. So, mo ni siya ang volume. And the distance dx is x since it is not given. And after nimo i-calculate nimo siya in a calculator nga applicable ani tanan, the final answer will be 6 times 82, 6.82 times 10 raised to the power of 6 joules. So, this is the final answer.
How much work is required to lift a 300-pound crate up a distance of 200 feet using a rope that weighs 4 pounds per feet? So there's two parts. The first part is we need to lift up the crate. So how much work is required to lift up a box or a crate? The work required is simply force times distance. And so the first is the weight of the crate, which is 300 pounds. And we live in and up by a distance of 200 feet. So it's gonna be 300 times 200 and that is 60,000 pounds times feet. So that's the work required just to lift the crate. How we need to calculate the work required to lift up the rope by a distance of 200 feet. So first we need to write an equation for the force that's required to lift up the rope in terms of x, and it's gonna be the weight density in pounds per feet times the distance that we're lifting it up. So the first equation is gonna be 4 pounds per feet times x, or simply 4x. So the work required is give me the definite integral from a to b. So from 0 to 200, we're gonna integrate 4x dx. So the antiderivative of 4x is 4x squared over 2 evaluated from 0 to 200. So 4 divided by 2 is 2. So we have 2x squared, and so that's gonna be 2 times. So 200 squared minus 0 squared. So 200 squared is 40,000. If we multiply that by 2, that's gonna give us 80,000 pounds times feet. So the total work required to lift up the crate along with the rope is going to be the sum of these two numbers. And so 60,000 plus 80,000 is 140,000 pounds times feet. So that's the total work required to lift up the crate and the rope. You just need to calculate the work required for each item separately and then just add it up.
Find the work done in pushing a car a distance of 15 meters with a constant force of 500 Newton. The formula is work equals force times distance. So substitute force 500 Newton times the distance of 15 meters. 500 times 15 equals 7,500 Newton per meter or 7,500 joule. So this is our final answer. Thank you so much for listening. Again, I am Charmaine Marie A. Arubo.
Isosilito Saruna in BSIE 1B.
I'm Clear Bakiran from BSIE 1B.
And we are the Group 3.